We know that prime numbers go on forever, but mapping their exact placement along the number line leaves you with chaotic static. At a global scale, prime density follows a clear curve, but zoom in to the local level and that predictability vanishes, leaving a sequence that defies simple patterns. For centuries, the search for a rule governing these numbers has focused on addition, trying to find the right number of steps to take to reach the next prime atom. We can examine the possibility that primes are frequencies rather than discrete objects. Treating the prime distribution as a continuous signal provides a framework to find hidden order where arithmetic sees only static. Finding that order requires moving away from the standard, additive number line and onto a multiplicative scale. On a logarithmic scale, we search for patterns that repeat every time the scale is multiplied. Here, distance is a measure of exponential growth and orders of magnitude, rather than simple counting. This creates a new map of prime distribution across multiplicative space. Researchers process this distribution using the same logic as a digital audio signal. This allowed for the application of audio engineering techniques to the raw statistical data of the primes. By treating mathematical data as an acoustic signal, we can use standard engineering tools to isolate structures that are otherwise invisible. Applying a low-frequency bandpass filter to this logarithmic data allows us to strip away the noise. The filtering reveals a dominant quasi-periodic wave with a massive repeating recurrence scale. We can measure the phase bands of this wave to track its distinct peaks and troughs. Primes cluster within these peak phase bands, while the troughs remain empty. Local prime density is being modulated and gated by this underlying wave structure. Primes actually behave just like a diffraction pattern. They are the visible result of multiple invisible oscillators combining through constructive interference. These oscillators originate from the Riemann zeta zeros, the specific values that define the frequencies of the prime distribution. In classical mathematics, these zeros were often viewed as a byproduct of the primes themselves. The zeros actually define a pre-existing spectral environment. This environment establishes a strict phase state, and primes only emerge where that phase allows them to exist. This makes primes the measurable physical reactions to a deeper geometric structure governing the number line. Ultimately, we can now see that the distribution of primes is a physical measurement of a highly structured mathematical spectrum.